studies have shown that classifiers perform better when they are ensembled, and they are actually more accurate than an individual classifier. Ensembles use several classifiers actually, and with each of them making a decision about the object, it becomes a rather nonlinear process. These individual decisions are aggregated in a combiner. The ensemble outputs a class label for the object. This is a continuous process, one which is abstracted from the Mosquito server of a message queue telemetry system with a Raspberry Pi or an Arduino reporting via Prometheus metrics into a Grafana InfluxDB time series database. So think about further dividing our data set and listing the data set. And by listing, I mean creating a tree, a hierarchical tree of our predictors. We're looking into the best set of features and the best classifiers, and looking at what are those sets of classifiers and the best combination of these classifiers that will give us the best prediction. And interestingly enough, methods of composing this are partitioned into meta algorithms, if you will. In this case, the data capping, by doing data cap list, we're exposing those capped data outliers. And these go over a method of further composing, further pruning, if you will. This is the ensemble pruning of reducing variance with bagging, reducing the bias with boosting, improving predictions with stacking. Methods can also be divided into parallel methods and sequential methods as well. But remember that we are looking into the group of weight majority voting, or the naive Bayes, as a classifier selection. The diversity of this is that it gives us the ability to manipulate the training parameters to the extent that the hidden layers receive order information, or information that is not as stochastic and random, but it actually follows a specific set of oscillators. As you can see, it followed a specific tidal pattern, if you will. Now, we treat this data frame object as that epoch, giving us first the classifier, in the sense that a parallel method is built upon the set of capped outliers from the data set, or the cleaning, and we call it the clean data set, and we access that specific time frame. And this is a method of sequentially generating, for example, a set of weights that is multiplied throughout the hidden layers, and then the output would be that activation function, or the sigmoid, the S curve, that is then used as the input for a stacked autoencoder, which has a base classifier. And in order for us to see this, we have to order, and this is the pre-processing, labeling the accuracy, the precision, as we saw before, and the goal variable, or the simple moving average. That goal variable will give us that index of where those values are oscillating to. And when we think about using a data frame of outliers that has been surgically removed from the data set, or clean, if you will, we're doing order-based pruning, where we're selecting an ensemble of order quality scores. Reduced pruning would be the sorting of classifiers by the classification error, and choosing several best ones. Kappa pruning is another one. Hierarchical, finding those quartiles where in the distribution of the cluster, can we order them in terms of their specific locality within that distribution? Can we make sense of those quartiles? And that's how we get to the lower, upper, medium quartile, being, again, the iteration of the outliers as the index for that specific local cluster or local set of outliers, distinguished from that global set of outliers. And thus we obtain an ensemble with individual classifiers, each returning of the training. These classifiers of the ensemble remain unchanged and then easily verified, as you can see, into 4 stages, again, if you want to keep dividing your information before you feed it to the neural network. Now, remember that this is very important. There's an option that meets most requirements when it comes to a type of neural network that will work in situations of extreme constant information. We call these the extreme learning machine, the ELM, which was proposed as an alternative learning algorithm instead of having multiple layers. And it is fully connected neural network with only one hidden layer, but without an iterative determination of weights. And it becomes exceptionally fast, mainly because it uses a random function and a pseudo-random or random function that captures the state of that epoch and compares it to the classification error. And from there, we can ask questions like, well, how many classifiers are necessary from here on? So should we have 500 and then prune the, or can we just parallel dispatch a sequence of training of classifiers and simultaneously finding the optimal combination? And for this manipulation of data provides high diversity and the accuracy can be all over the place. But we call this bootstrapping or a bagging of classification. In another way, we're generating the source data sets, we're arranging predictors by information importance, we're training and testing the ensemble classifiers, we're combining the individual output of the classifier, we're ensemble pruning, and then we're searching for that metric of the ensemble classification quality, meaning that divergence or convergence of that centroid to that local node that we're interested in, and that gives us an information of the global outlier